So we'll move to stresses in a beam now. That's the next topic here. So if you recall, we have already covered that moment equals EI W double prime, or the curvature. So EI times the curvature equals the moment. And we also covered that the strain equals linearly, is linear and proportional to the curvature. So we covered that. We also covered that the stress equation is sigma xx equals E times epsilon xx. But epsilon xx is Y times the curvature term, so that's what you get for stress. So that's the equation I had not shown you before, but it's pretty much just plugging that in here. And what I can do a little trick. What if I divide the left-hand side with the right-hand side? If I divide the left-hand side, I get sigma xx divided by m. If I divide the right-hand side, E cancels out, the curvature cancels out, and you get the equation that you've seen before, which is sigma xx equals my over I. Everybody here has seen that formula, my over I. That's where it comes from. That's what the stress is. And what that's saying is at the neutral axis where y is 0, you have no stress. But in the outer fibers, you get the highest stress as possible, farthest away from the neutral axis. Any questions on that? Stress derivation. That's the question you'll be using. What if you're worried about the sign convention? What do? Do you freak out? What do you do? Or you look at the problem. You look at the problem. I have a beam. I apply a load P. I expect it to do this. You agree? So if the beam is like this, right? Which side is in compression? Which side is tension? This should be compression. And this should be in tension. Any questions on that point? Is that clear? Yeah? Use physics. Don't get stuck by getting worried about things. Let's look at shear stresses in a beam. There's this formula here that you may have seen before, the shear stresses in a beam. So you'll have shear stresses through the thickness, and that's going to be equal to the shear force applied divided by I, which is the moment of inertia, times B, which is the B width, and then times this Q here, which is the first moment of inertia. And so shear is equal to V times Q divided by IB. So where does that formula come from? So let me start with taking a little section here. So I took a little section here, dx. Moment here is m. The moment on the right-hand side is m plus dm. And notice that y is going downwards. I'm doing that on purpose so that your understanding is irrelevant of what convention I use. I don't care what convention I use. It should be consistent to what's going on here. The shear is going up. V plus dV is going downwards for equilibrium. That's the only way it can be in equilibrium. And then what I can do is study what is going on. So if I look at the left-hand side of this beam, this left-hand side here has a stress distribution that's my over I. On the right-hand side, because I have m plus dm, I have m plus dm times y divided by I. Any questions on that? So sigma 1 is on the left-hand side, and sigma 2 is on the right-hand side of that beam. Any questions on that little cut that I made? So you can understand the shear stress. So if I do balance of forces, I have tau x y times the area, which is the width of the beam, which is B, times dx. So that's what you have there as the shear force here. And that has to be balanced by the shear forces on either side of the beam. And these forces need to be in total equilibrium. You can see here the shear is acting to the left, and then this sigma 1 and sigma 2 is going here on these sides of the beam. So it's a summation of forces in the x direction. That's what this is. Again, that's why you have a shear of tau xy times dx times the width b. That's your total force moving to the left. While these forces here are the forces acting on each of these sides of the beam, and those are the formulas for that. If I plug in what sigma 2 is and what sigma 1 is, I get this formula here. And you'll see that m over I cancels out with this m over I. So it cancels out. and then get that tau xy b dx equals dm over I integral from y to h y dA. You also notice that and I can divide this by dx, by the way. So I'll divide by dx, and when I do that, and I divide by b also, I get that tau xy equals this formula right here. You also notice that dm dx is v, and so now what you get, and then if you call this geometric property q, then you get this formula that shear equals v times q divided by ib. V is a shear force acting on that cross section in here, for example. And q is the first moment area, I is the second moment of inertia, while b is the width of the beam. That's where the formula comes from, and I'll give some examples coming up so that the concepts become even more clear. In this case, what I've done is I've calculated shear stress through the thickness of a not a composite beam. And so if you do the integral for rectangular cross section, you get minus b half to b half, y to h. And when you do this integral, you get that the stress is actually parabolic through the thickness. And the highest stress actually occurs at the neutral axis of this beam, which is actually the lowest stress for sigma xx, the bending stress, because the bending stress is zero at the neutral axis. So the shear force, shear stress is tau max equals, for a rectangle, the highest shear stress becomes 3v divided by 2bh. You can do the calculation and check it out. But all you have to do is plug in y equals 0 here, and you get vh squared divided by 2i. I for a rectangular beam, I believe, is 1 over 12 bh cubed. When you plug it in, you will get the formula I'm showing you here, but that's how you will do that. So what we then apply this for a particular problem first. I'll cover it for a problem where I have a beam, and this beam is pinned here and pinned here, is subjected to a triangular distribution of load, just for fun. It asks you for what is internal force, stress, shear stresses, and normal stresses at point B. That's a question. And then it's asking you, yeah, that's really what it's asking. So on the bottom here, it's showing you that I have a load applied of 180. And let me explain where that 180 comes from. The height is 60. The length here is 6. So 6 times 60 is what? 6 times 6, 360. 360 divided by 2 is the area under that triangle. That's 180. So that's why that 180 shows up, because that's the total force that's effective due to the triangular load distribution. Again, 1/2 times the height, which is 60, divided by this width, which is 6, gives you 360. 360 divided by 2 is 180. That's the load applied. Where do you place that? You place it 1/3 from this edge or 2/3 from this edge, this corner. Because this is 6, 6 times 2/3 gives you about, you can do the math. What is that? 4. So 4 meters. That's what that point is. This rotor is being removed and put RA, and this point is being removed and you get RD. So this is really the breakdown of the problem, a free body diagram that's going to help you move forward looking at this problem. So now I'll take moments about A, and if I take moments about A, I'm able to find the reaction force D, because this RA does not contribute to the moment at A. You get RD times 12, which is what you see here, and then you have 180 times 6, which is what you see times 4, is what I said. So you can get RD out of there, which is 60, and if this is 60, and that's 180, that has to be 120 from summation of forces in the y direction. Any questions on very basic stuff covered in a more basic course? Is this clear? Now that I have that, I'm ready to find out what is going at point B, because the question was, what is the shear stress and normal stress at point B? So I can look at that now because I know the reaction forces. I can now do a free body diagram, cut it right there exactly where I need it. And we know we have a shear force and a bending moment. So if this force, the height at that point in time is 30, by the way. You can check that yourself. So if this is 60, about 3 meters out is 30. That's the height. So 30 there. I know the reaction force now. The reaction force was how much? 120. So well, that's 120. I'll let you do the math, but when you do it, you get the V, the shear force V is 75. And you may ask, where's the 45 coming from? Well, 30 times 3 is how much? 90 divided by 2. So 45 should be the shear force, the force acting downwards. So that's where the 45 is coming from. And 120 is from this reaction force. So this shear force going through this cross section is 75. What about bending moment? Bending moment, I'll some moments about this point, so I have to worry about the shear that I don't know anything about, or now I know it's 75. Back and do the calculations, 45 times 1, because the force that you apply here needs to be 1/3 away from this edge. And since this is 3 meters, 1/3 of 3 meters is 1 meter. So this distance is 1 meter. So 45 times 1 meter plus the moment here. And then you have this 120 times this distance that also contributes to a moment of 3 times 120, because it's moment arm distance times the moment, the force applied. That's what that is. So that's 360 minus 45. And then you can get the moment of 315 newtons per meter. Any questions on these basic calculations that was covered in a different class? Everybody has seen this? Good. So it's a kind of good review, top level, right? But now what I can do, I know the stress is my over I, and I know shear stress is VQ divided by IB, and the cross section is given to us 10 centimeters by 5 centimeters. One thing you want to keep in mind when you go to industry, I already covered this, but there's been countless of errors in industry due to unit problems. That's meters, that's centimeters. Do you want to do the analysis and plug in hybrid units? Centimeters here, meters here, newtons here. Make it more cool. Put pounds once in a while to see what happens. I've seen that happen too, by the way. And do you think those people are not very sane when they do that? That's a trick question. Are the people making those mistakes crazy? They're not crazy. They're making pretty significant mistakes. Pounds, newtons. You don't think they're crazy? Huh? Thank you very much. I make those mistakes. So call me crazy because I make those mistakes today. It's normal. And that's why in industry, you want to have a peer review. When you have done an analysis, it's very important to have a buddy that can, and I call it the buddy system, where you do your analysis and you have somebody come in and say, hey, can you look at what I did to make sure I didn't miss something? Because I'm not perfect, right? So having that is very helpful. They can find things you cannot find. And that's actually very helpful. I am crazy anyway. That's great. We'll move on here to the next slide here. And look at the calculation. The inertia, moment inertia for a cross section is 10 by 5 is easy. It's 1/12 BH cubed. So that's a very easy calculation. You guys can do it, the calculation yourself. You'll get 4.17 E minus 6 meter to the fourth. Good news, I made the unit conversion is meters. Bad news, I don't know if this number is right because I could have misused my calculator, right? But that's okay. Y equals 1/2 times 0.1 meter. Because you need to calculate what is the farthest distance away from the neutral axis. And that's going to be, the neutral axis is here. So half the distance of H, you have to calculate what is the farther distance from the neutral axis. So that's 5 centimeters. So plug that in, you get 0.5 meters, I guess. I'm concerned I made a mistake, actually. You check it at home. And then moment is 315. So there you go. You know the stress. Shear stress is VQ over IB. I know the shear is 75. I calculated here, remember, from this free body diagram, 75 and 315. So I have that shear. 75, I know B is the width is 0.05. It's 5 centimeters. 5 centimeters in meters is what? 0.05, right? Good. I actually wonder if this is right. Yeah, that's right. The inertia is the same. That doesn't change. Q max is just H squared minus Y squared divided by 2B. You can calculate it. That's going to happen in the center right here in the neutral axis. Center is the wrong wording, by the way, the neutral axis. And then the max shear stress gives you 0.045 megapascals. So that's the solution for this particular problem. With that said, I'm going to move on to the next lecture.